Hello and welcome to this episode of Physical Attraction, where we'll be talking about cold fusion, one of the biggest scientific scandals of the 20th century. The physicist and philosopher Thomas Kuhn described what he called the essential tension in the sciences and in scientific research. It's what he called the tension in the sciences between tradition and innovation. Most scientific research builds on, expands, or refines the existing picture of the universe that we have. It forms a part of other theories. It uses the results and the ideas of those theories to explain or explore some other aspect of reality. It refines them in a way. It's evolutionary rather than revolutionary. Very often this is how theories are developed, by a long series of different contributions from different individuals, conducting experiments, observing, and trying to fit their results into the existing frameworks, or using their results to expand those frameworks slightly, applying them to solve new problems. You're part of a scientific community and a school of thought about how the universe behaves. But just on occasion, it's necessary to totally discard the existing theories about what might be possible. Just on occasion, your experiment has produced results that really cannot be explained by the existing theory or experimental error. Every now and then, there is some innovative idea that flies in the face of basic principles of the previous theory. You think of Copernicus and Galileo. You think of Einstein's theory of relativity. You think of the revolution in quantum mechanics that inspired so much of what Kuhn wrote. These are not mere tweaks around the edges of the old ways, but entirely new, first principles, reimaginings of how the universe functions. Particles are no longer little billiard balls that fly through space, but probability wave functions that have no fixed position, momentum, or energy. Time is no longer a constant ticking clock that moves at the same speed for everyone in the universe. Instead, it depends on who's got the clock, and how quickly they're moving relative to each other. These are not minor details, but fundamental reimaginings of what's possible. And so we have the essential tension. When to work within the frameworks and the theory that already exists, and when to throw the whole apparatus out of the window because it no longer works. In light of this essential tension, when someone comes up with a brand new theory, how does the scientific community respond? Does it stay reactionary, wedded to the old paradigm and the old way of viewing the world until some truly convincing evidence is presented? Or does it embrace the new theory and the innovation and explore its consequences? How can you tell if this new theory is the next quantum mechanics, or just the raving of a crackpot? The sociologist of science, Professor Harry Collins, notes that one of the ways you can identify a fringe scientific belief is what he calls pathological individualism. In other words, people with fringe views reject virtually everything that the mainstream believes in, even if they have no alternative explanation and no valid criticism of what already exists. It's not about expanding the theory, it's not about revising the theory or being right. It's about being right when everyone else is wrong. That's the pathological nature of the individualism for many of these fringe scientific beliefs. The tales of these pioneers of science, these lone revolutionaries who are smart enough or lucky enough to revolutionise their individual fields, these are wonderful tales. It's no wonder that they seduce some people into believing that they might just be one of these revolutionary figures. In the field of nuclear fusion in the 1980s, with the stakes so high, with multi-million-dollar experiments trying and failing to produce net energy, it's easy to imagine people wanting to overthrow the paradigm of ever larger and ever more complex and expensive tokamaks and laser fusion devices to create something new, innovative, and revolutionary. Science faces this debate endlessly, this endless tension. On one side you will often hear people denounced as fraudsters, crackpots, attention seekers. On the other side you will hear the mainstream denounced as old fuddy-duddy reactionaries who are jealous of real genius. Sometimes, and I should say that this is far less often than people would like to think, but sometimes the people going against the mainstream are indeed correct. But the story of cold fusion was not one of those times. It all began, at least to the general public, on the 23rd of March 1989. There was a press conference at the University of Utah. That's the first remarkable thing. Scientific breakthroughs are usually announced with big splashy papers in peer-reviewed journals. Yes, there's press attention and a press release if the work is significant, but you rarely announce what you found without some concrete data and details to show people. Something that hasn't been peer-reviewed by your colleagues isn't really worth announcing to the public yet. In this press conference, two electrochemists from the University of Utah, who few people had heard of, especially in the physics community, were called Fleischmann and Pons, and they announced that they had achieved sustained nuclear fusion reactions. Their new method apparently didn't need a colossal tokamak filled with plasma and complex twisting magnetic fields. It didn't need lasers or beams of particles to heat that plasma up to millions of degrees. Instead, they announced they could achieve fusion at room temperature, in a basement laboratory using an apparatus that fit on the top of a table and cost just a few $100s. All you needed was a battery, some water, and the crucial secret ingredient, palladium metal. They weren't planning to announce too many details straight away, not until their device had been patented anyway. After all, what Fleischmann and Pons were announcing may well be the new means of making power, cheaper and cleaner and safer than anything attempted before, and they wanted to make sure that they were going to reap some of the vast financial rewards from these devices. The Nobel Prize that they were sure to win for their discoveries was just the icing on the cake. But they did announce that their fusion reaction had produced, quote, heat, neutrons, tritium and helium, the expected byproducts of fusion reactions. The test tube apparatus that they'd used was under constant guard, as the scientists themselves appeared on magazines and TV shows, catapulted to fame by the discovery that would change the world. In their press conference, they were accompanied by the president of the university, one Chase Peterson, who was not one to undersell the significance of what they had achieved. He said that the discovery ranked up there with the discovery of fire, the cultivation of plants, and the uses of electricity. No big deal then. Meanwhile, the scientific community responded. Some were immediately cynical. Well, wouldn't anyone be if they'd spent decades working on the immense complexity of magnetic confinement fusion, only to be pipped at the post by a couple of chemists that had rendered all their work obsolete, using equipment that you might find in a high school lab? But this wasn't only a fact of people thinking that their endeavours to build vastly complex tokamaks might have been a waste of time. The thing is, this really contradicted all of the consensus about fusion. How on earth were the nuclei in Fleischmann and Pons' experiment getting enough energy to overcome the Coulomb barrier, the electrostatic repulsion between the nuclei? We've described how this usually requires pressures and temperatures comparable to those you find at the heart of the Sun. In tokamaks, you have to produce plasmas at temperatures hotter than anything else in the solar system. This is all just to give the particles enough energy to overcome that electrostatic repulsion. The idea that you could circumvent that with some batteries and a piece of metal seemed far-fetched to say the least. Equally, the fusion scientists knew all too well how easy it was for there to be false dawns, to see something that looked like a promising avenue to fusion, only to realise that it was far more complicated than you had initially hoped. Yet, without any details of the experiment, there was always a vague possibility that they had indeed discovered some completely new and rare effect. Now, Fleischmann and Pons might not have been world famous, but Fleischmann was a Fellow of the Royal Society, a high scientific honour for British scientists, given usually in recognition of important scientific work. Between them, Fleischmann and Pons had dozens of papers previously published in reputable scientific journals. So these weren't obviously fringe crackpots, but well-established, if not world-famous scientists, and this made their work much more difficult to completely dismiss out of hand. Yet the fact that the scientists were hearing about this first on the evening news was unusual, to say the least. At the same time, in other quarters, where people didn't know how to assess the likely validity of the science, people were concerned about the military applications of the new technology. After all, this palladium electrode that was needed to get these fusion reactions to work, palladium is a rare earth metal. Would there now be wars for control over palladium resources? In our Buzzkill episodes, we talked about how fusion reactions and the hot neutrons might allow people to create fissile material for nuclear weapons from more innocuous isotopes. If anyone could use this technology to create nukes, then the delicate balance of the world that appeared to be arising in 1989 as the Soviet Union collapsed could be thrown into chaos, disarray, and war. After all, if you can produce thermonuclear reactions and these hot neutrons that can produce radioactive isotopes using apparatus that you might be able to buy for a school chemistry lab, then getting rid of nuclear proliferation would be an extremely difficult problem. The situation was compounded the very next day when a rival group of scientists, headed by Stephen Jones at Brigham Young University, also in Utah, just a few miles from Fleischmann and Pons, announced that they had been investigating this cold fusion for years and had conducted a similar experiment that had shown signs of fusion by producing neutrons. Suddenly, it seemed as if Utah was, improbably enough, the new capital of energy research, and the state and then federal government began pouring millions of dollars into commercializing and exploiting this new discovery. Of course, we now think of cold fusion as one of the most infamous and embarrassing episodes in the history of science. An enormous amount of hype over scientific results that were, at best, a huge mistake and a misapprehension, and at worst, outright fraud. Fleischmann and Pons' experiment wasn't producing fusion at all. It was precisely as impossible as all the naysayers in the mainstream had said it would be. But for its impact on the history of fusion science, and as a fascinating example of when science goes wrong, it's worth going into this story more deeply. How did this happen? How did it unravel? How were so many people taken in by the false results? And how can we avoid similar fiascos from happening again? To do that, it's worth looking into what Fleischmann and Pons were claiming in more detail, and why they couldn't be dismissed completely out of hand. Palladium, the secret ingredient for their cold fusion experiment, is an interesting element. You might have some in the catalytic converter in your car's exhaust pipe. It's an excellent catalyst for chemical reactions, owing to its unique crystal structure. It brings different atoms closer together, allowing for chemical reactions to take place more quickly, as they fall in this nice crystal lattice. As early as the 1920s, shortly after Rutherford had discovered the nucleus and people had begun to theorise that helium was made up of two hydrogen atoms squished together, scientists were trying to use palladium to help build hydrogen into helium. Palladium is very good at absorbing hydrogen. It can absorb approximately 900 times of its own volume of the gas, soaking it up like a sponge soaks up water, where the hydrogen atoms sit in the gaps in the lattice structure. This property has lots of people very interested in palladium today as a source for hydrogen fuel cells. One of the problems with using hydrogen as a fuel is that its energy density is very low, so you require great big tanks of the stuff to get there. But of course, if you could cram it all into these palladium fuel cells, you might then be able to extract it from a relatively smaller device. Some experimentalists called Paneth and Peters in the 1920s had attempted to cram as much hydrogen as they could into a palladium sample, in the hope that it would force the atoms close enough together to react and produce helium. Sure enough, they detected minuscule quantities of helium, but not enough at that point to be practically useful in the airships of the day. A few years later, another scientist called Tandberg had the bright idea of adding electrolysis into the mix. Electrolysis is used today, all the time, to produce hydrogen from water. You pass an electrical current through water, which breaks the molecular bonds between hydrogen and oxygen in that water. The hydrogen atom loses its electron, becoming positively charged, while the oxygen atom gains an electron and becomes negatively charged. They're then attracted to either end of the circuit, to the positively charged anode or the negatively charged cathode. Tandberg thought that perhaps using these electrostatic forces, which would attract lots of hydrogen towards the cathode, might result in enough pressure and density to produce a significant quantity of helium. He even tried to patent his device, but was told that his description was far too vague. No one could possibly be able to reproduce the results from what he'd said. As nuclear science progressed further, and it became clear to everyone that you'd need deuterium to fuse into helium, Tandberg repeated his experiments with heavy water. His aim here was nothing less than producing energy from fusion. He even warned colleagues that if his calculations were correct, the machine might explode with considerable force. Of course, Tandberg never managed to achieve fusion with hydrogen or deuterium. It later turned out that the initial detection of helium was faulty. The detector had simply been detecting some ambient helium that was sitting around in the atmosphere that had accumulated onto the device. There was no evidence that the palladium device of Tandberg had ever produced helium from hydrogen at all. The amazing thing here is that all of this scientific controversy was done and dusted by around 1930, yet it bears a striking resemblance to the experiment that Fleischmann and Pons attempted in 1989, nearly 60 years later, to such fanfare, with the same ultimate results. Of course, Fleischmann and Pons didn't know this. They had long careers investigating electrochemistry, the properties of liquids when you pass electrical currents through them. When they realised, over some whiskey, that it might just be possible to use those electrical currents to exert extreme amounts of pressure on deuterium in a palladium catalyst, and maybe, just maybe, create nuclear reactions, they couldn't resist giving it a try. According to Frank Closer's excellent book on cold fusion, Too Hot to Handle, Fleischmann said, "It's a 1,000,000 to 1 chance. Shall we do it?" The initial experiments were the kind of 1,000,000 to 1 shot pet project that many scientists probably have. Not realising that their work had been anticipated 60 years before, the pair didn't want to tell anyone about their ideas, nor did they think that anyone would possibly fund such an unlikely experiment. So they bought the equipment and funded the experiment themselves with around $100,000 of their own money. According to later accounts from the pair, the first time they really thought they were onto something was in 1984, when their test apparatus exploded overnight. They didn't immediately think that this was necessarily a nuclear explosion. After all, there were plenty of ways that a gas build-up or pressure explosion could have occurred, but then they didn't feel like they could rule out the release of energy from fusion either. A few years after this, they had started to report and reliably measure a small heat excess from their device. If the heat was genuinely being produced by fusion and wasn't a systematic measurement error or caused by ordinary chemical reactions, then they would have expected to produce plenty of neutrons from the fusion reactions that would irradiate their experiment. But their radiation detectors only measured a slight excess, far less than the billions of neutrons that they would have expected if all the energy came from fusion. Nevertheless, by this stage, in 1988, Fleischmann and Pons, perhaps still remembering the curiosity of that explosion years before, were looking to take their pet project more seriously. To do that, they needed funding, and to get that funding, they went to the US Department of Energy. As its current secretary, as I write this, Rick Perry, wanted initially to abolish the DOE as a presidential candidate, found out, a big part of the DOE's remit is in nuclear weapons and nuclear research in general. The DOE were in fact already funding some research into cold fusion experiments by that one Stephen Jones at Brigham Young University. The DOE weren't going to just throw money at any project, so they wanted to insist that the grant application was to be peer-reviewed. Other scientists would need to look at Fleischmann and Pons and what they were doing and whether it had any prayer of success. The DOE, of course, couldn't think of anyone better than Stephen Jones to look at this experiment, the very man who was working on similar experiments in the same state, and who had been interested in another kind of cold fusion, muon-catalyzed fusion, for many years. This moment is really at the root of the cold fusion chaos that followed. Once Jones had peer-reviewed the work of Fleischmann and Pons, they entered into an increasingly frantic race to be the first to get good, reliable results and to publish the findings. After all, if there were going to be Nobel Prizes, fortune and fame, it would go to the first people who published, and not those who followed up. Things get a little murky here, because every character in the story obviously has their own motivations, their own side, and their own story even about precisely what happened. Usually to save face, or to defend the reputations of colleagues, and also, due to faulty memories, people can't remember everything that occurs perfectly. It seems as if, perhaps at first, the two groups entered into a loose collaboration, with Jones offering the Utah pair the use of his neutron detector. Soon enough, though, the race heated up and they started being a bit less cooperative. They had agreed that when the experimental results were all ready and had been fully analysed, both groups would publish a paper in Nature together, announcing their joint findings. But there was deep distrust between the groups. Some from the University of Utah accused Jones of stealing the idea for his cold fusion experiments from the application he'd received, which would obviously be plagiarism and a big no-no. Jones sent in an abstract, that is a brief description of a project, to the American Physical Society, saying that he had discovered a new form of cold fusion in February of 1989. This isn't quite the same as a publication, but it's usually saying that you're going to intend to publish your results soon, and trying to stake out some prior ground and saying, this is what I was working on as early as this when I submitted this abstract. In the meantime, Fleischmann and Pons were trying to measure neutrons coming from their device in early 1989. The most obvious products of nuclear fusion, after all, were neutrons and heat. They'd seen the heat, and now they were looking for the neutrons to confirm their findings. But this experiment, the final experiment, just a month before the press conference was announced, was rushed. A proper experimentalist would have taken a proper reading of the neutron background. Some neutrons are being produced all the time by traces of radioactive material, by cosmic rays that constantly bombard the Earth's atmosphere, and so any good neutron detector will always measure a few neutrons from time to time. But the number of neutrons that will be measured will vary from place to place. Fleischmann and Pons didn't have time to run repeated background readings for 50 hours without running their experiment, and so, to get their background reading, they had two neutron detectors running, one at the site of their cell and one 50 metres away. They found that the readings around their cell were approximately 3 times higher than the background, and decided that this was evidence that the experiment was producing neutrons. You might be thinking, hang on, 3 times the ordinary background noise? Surely, if fusion reactions are generating the energy here, there should be a huge number of neutrons. After all, isn't the neutron flux enough to destroy the metal walls of tokamaks, and now you're saying that it's barely detectable? And yes. In fact, as many experimentalists would find out later, it's quite possible to see variations on the neutron reader this high from pure fluke alone. It's hardly the 95 to 99% confidence that physicists typically want to report results as a sure thing. For me, this is the most inexplicable bit of the whole announcement. So Fleischmann and Pons had found 2 vague pieces of evidence for fusion reactions in their device, the excess heat and the neutrons. But the fact that they had these 2 lines of evidence didn't really make their claim any more strong, because they contradicted each other. They weren't consistent at all. A more thorough experiment would have measured the energies for the neutrons. Were these neutron energies consistent with that which would be generated by fusion? To their credit, Fleischmann and Pons did indeed try to measure the energy from the neutrons. Harwell Laboratory, the same place with the infamous Zeta reactor which you'll remember from previous episodes, had some of the best neutron measuring equipment in the world. They'd hoped to send their whole apparatus over to England for someone to take the results in a hurry, but it was classified as a radiation hazard and held up in airport security. With this effort frustrated, another hurried effort to measure the neutron energies measured what the team hoped were gamma rays that were being produced as a byproduct of the neutrons hitting the apparatus itself. So the idea here is that you produce these hot neutrons, they hit the apparatus, they make these gamma rays, you detect the energy of the gamma rays, and that energy is related to the initial energy of the neutrons because they're sort of what you get when these neutrons scatter, so you can kind of calculate what it's supposed to be. The experimentalist who measured the results, originally employed as a radiation safety officer at the university, did so under extreme time pressure in just 2 days, but did seem to find a peak that might be consistent with the energies of the neutrons that were being produced. At the same time as Fleischmann and Pons were trying to confirm what they thought they'd seen, the heads and administrations in the respective universities were meeting up for a summit. Already they were getting wildly ahead of themselves about the nature of the discovery. Fleischmann and Pons had observed a small amount of excess heat, maybe just 25% more than they had expected. After all, this device would heat up when you pass the electricity through the water and the electrolysis takes place. But what they were finding was a slight excess that they couldn't explain. And they found a low hum of neutrons with one hastily run detection experiment. It was certainly an interesting anomaly, and something that needed explaining, but in scientific terms this is hardly proof of anything, let alone something so unlikely and unexpected to begin with. Remember, extraordinary claims require extraordinary evidence. If they were saying that they had found perhaps some new chemical reaction, well, new chemical reactions can be discovered from time to time. If they were suggesting that there was some fault in the measurement apparatus, that's perfectly plausible based on their results. But to claim that you had discovered an entirely new form of nuclear fusion, and one that was somehow allowing these huge Coulomb barriers to be overcome, you really need really convincing evidence before you can overturn the laws of physics like that. But to the university administrators, this was already a limitless source of energy with billions of dollars at stake. And for those in the university, the motivations are obvious too. Perhaps they were a little frustrated by the reluctance of the scientists to announce their findings, and they were thinking of the money for the patents, the funding for future experiments. Imagine being the people who let this opportunity slide or let someone else take over. It'd be like being the record executives who didn't sign the Beatles. So you have to conclude that it was really a perfect storm. With pressure on them from the head of the university to announce the discovery so that they might benefit, with starry-eyed dreams of being the heroes of this new form of energy, and with fears that they might be beaten to the punch by someone who might have stolen their work, Fleischmann and Pons did ultimately decide to go ahead with the press conference. The days running up to the press conference were chaotic for Fleischmann and Pons. 2 days beforehand, Fleischmann received word back from Harwell where one of his experiments had eventually arrived. They had detected no neutrons. Pons reassured him. Perhaps they'd set up the experiment incorrectly. It was sensitive and it didn't seem to work every time they ran the test, so it's possible that the scientists at Harwell had bungled. Apparently, the scientists had some misgivings, as you'd really think they should have given the enormity of what they were announcing and the shakiness of their evidence. But the momentum of events was running away from them and running away with itself. At least this is what they say. But Fleischmann hardly helped himself. He tipped off a reporter for the Financial Times in the UK, where he lived, about the results of their bizarre discovery. Because of a strange confluence of holidays and time zones, this reporter published the story on the morning of the press conference, before the press conference came out, even though it was supposed to be a secret. This meant that by the time they did their press conference, journalists had caught wind of what they were going to announce. So over 200 journalists descended on the University of Utah to see the announcement, a truly colossal number for what might be an ordinary scientific press conference. Even as results were coming in that day that cast doubt on their shaky experimental findings, the cold fusion hype machine was whirring into overdrive. Fleischmann, for his part, just wanted to get through the press conference and then return home to think things through. Unfortunately for him, he didn't appreciate quite how dramatic things were about to get. Of course, it's worth saying that, as ever, the media didn't help. For example, the Daily Telegraph in the UK reported that you could build Fleischmann and Pons' apparatus at home for around £90, resulting in the Harwell laboratory being flooded with calls from members of the public, asking for advice on building their own cold fusion reactors at home. Meanwhile, plenty of more reputable labs were trying to repeat the experiment, leading to a flurry of contradictory results. Some people saw the excess heat, others didn't. Some universities seemed to detect neutrons in their apparatus. Others didn't. Some universities saw an excess heat signal. Other groups claimed to have detected tritium, another expected byproduct from the reactions. The fact that the apparatus was easy to build, or at least try to build, was partly to blame here, as it allowed dozens of institutions to conduct their own hasty experiments. All of these experiments were conducted very quickly in the week or two after the press conference, without full access to the details of the setup. None of them demonstrated a consistent set of results. You can see here something that plagues many of the sciences, which is what you'd call publication bias. In particular, when you look at the biomedical sciences and creation of medicines and so on, if your result of your trial is positive and it says X medicine can be used for Y product, then it's more likely to be published than another negative result. Also, it's much more difficult to rule something out than it is to rule it in as a possibility, if that makes sense. If you were trying to conduct a really, really thorough experiment, replicating the setup of Fleischmann and Pons, and you couldn't detect any heat and you couldn't detect any neutrons, well, you couldn't be sure that that meant that none of them existed. Perhaps you just messed up the setup somehow. But if you did replicate their experiment and seemed to see the same results, well then you could announce it straight away. And so there was this huge contradiction where some universities published results saying that they'd actually repeated their experiment successfully and others didn't. Things got much, much worse for Fleischmann and Pons when details of their work were first presented to a large scientific audience at the Harwell lab. There they showed the gamma ray measurements. This was supposedly the killer piece of evidence that their neutrons genuinely came from fusion reactions. But they didn't look anything like what the scientists were expecting. For a start, they had expected to see several small peaks from the various different reactions that were taking place. Instead, they saw just one peak. They had been interpreted by Fleischmann and Pons as evidence from neutrons for fusion, but it was in the wrong place. The gamma rays from the deuterium should have occurred at 2.22 megaelectron-volts of energy, but the peak was at 2.5 megaelectron-volts. This was obviously wrong, as it was more energy than should be released in this kind of fusion reaction, and it was not clear where it was supposed to come from. The peak was also the wrong shape. Experts in these energy spectra know the sort of general background that you're supposed to see, and they didn't see any of that in these measurements. It was clear that these measurements were wrong. Yet a few weeks later, when the paper came out describing this experiment, not in Nature but in the Journal of Electroanalytical Chemistry, the peak had mysteriously moved back to the correct spot. Yet Fleischmann and Pons hadn't corrected their mistake everywhere. The figure of 2.22 megaelectron-volts still appeared in the paper. This really was the first indisputable, outright evidence of actual scientific fraud from the pair, the mysterious moving peak. Everyone will remember a few scientific results that got an awful lot of attention from the media at first, but later turned out to be mistakes. I remember a few years ago when the faster-than-light neutrinos were announced, but of course they turned out to be experimental errors due to a miswired circuit. In that case, to be fair, the team who discovered them said that they thought it was most likely an error, but that they published the results to see if anyone could help them work out what it might be. Of course, that didn't stop people from reporting it as laws of physics overturned by new experiment. At this stage, with all the doubts and misgivings about the science behind their experiment, the inconsistencies and the confused results, Fleischmann and Pons should not have announced that their work with the fanfare that it had. Even after it had started to be criticised, they should have admitted that they weren't sure. But it seems as if events had spiralled out of all control. With dozens of conflicting results coming out from different universities, some of whom had apparently reported heat and neutrons in those earlier weeks, maybe Fleischmann and Pons perhaps had reason to hope that the cold fusion phenomenon was real, and that the inconsistencies in their experiments could be ironed out. Naturally, scientists working on hot fusion, especially those who had spent decades trying to crack this problem and knew just how hard fusion was to get right, were amongst the harshest critics of Fleischmann and Pons. Some scientists at MIT, who knew well the spectrum of energies from gamma rays that were supposed proof of neutrons, scoured the TV footage of the instruments to try and find details of the experiment to disprove it. They went so far as to reconstruct the gamma ray spectrum from a brief shot of it on video, noticing that the peak was in the wrong position and not surrounded by reliable measurements from other reactions. Some may have hacked into Pons's email account. Those in the cold fusion camp knew that they would cause waves. After all, if they were right, there was no need to spend billions of dollars building tokamaks to get fusion to work. Funding was already being diverted from hot fusion projects to cold fusion in those early weeks. Things got even worse when they presented their research to the American Chemical Society. At first, Thanks to some classic rivalry between the sciences, the chemists were sympathetic to the idea that perhaps they'd succeeded where generations of genius, smart-aleck physicists had failed. There was a huge amount of media hype surrounding the experiments. Yet a question quickly arose. Why hadn't they run an obvious control experiment? Ideally, in a control experiment, you take measurements where things are exactly the same, save for the one difference that you're trying to measure. Fleischmann and Pons were attempting to measure deuterium nuclei fusing together with a palladium catalyst when electrical currents were passed through heavy water. That is, the heavy water that has lots of deuterium nuclei in it, as part of their heavy water. If you replace the heavy water with ordinary water, you shouldn't see any fusion because there will be barely any deuterium in the device, but you can keep the apparatus running with its electrical current and palladium cathode in place. So one of the chemists basically said to Pons, "Why didn't you do this? Why didn't you just replace the heavy water with water? Then you'd know if there was any chemical reactions or measurement error going on, and if only deuterium seemed to produce a fusion reaction, that would back up exactly what you expected." But when they asked why this wasn't done, Pons's response was concerning. He said, "We do not get the total blank experiment that we expected." In later conferences, both of the scientists would refuse to talk about experiments with ordinary water altogether. In other words, Fleischmann and Pons's apparatus appeared to be measuring fusion reactions when there was nothing there that could fuse. How could they possibly be sure that any of the heat or so-called neutrons that they were observing were really from cold fusion reactions in that case? That's the kind of discrepancy that makes you sit up and notice. Combine this with the fact that, if the heat was genuinely being produced by fusion reactions, the scientists expected to see millions of times more neutrons than they were actually observing. Soon enough, the universities that had reported corroborating evidence began to back down or tone down their claims. They couldn't produce the results consistently. The excess heat had dropped off to much lower levels. There was a particular neutron detector that had been used by plenty of the original groups to look into cold fusion. This neutron detector was designed to deal with signals from billions upon billions of excess neutrons at a time, the kind of signals that a genuine radioactive source or fusion reactions might give you. Under these circumstances, when they were measuring huge fluxes of neutrons, the neutron detectors functioned really well, so no one had ever really noticed a problem with them before. But it turns out that small temperature fluctuations could lead to small excesses in the neutron detectors, the type that Fleischmann and Pons had seen and taken as evidence for fusion. When some of the universities had set up their own experiments and then controlled the temperature around the fusion neutron detector, they saw the neutron signal disappear. They'd been measurement errors all along. Nature rejected the joint papers that were submitted from the two Utah universities, telling them to go away and try again. This is the part of the story where Fleischmann and Pons should have admitted their doubts and resolved to perhaps go away and work on the experiments some more to respond to the criticisms that were being levelled at them. The fact that they didn't, and carried on in what must have been increasingly desperate hope that they really had seen something, including quite probably falsifying those results in the journal paper. I mean, this is close to fraud, and if it's not outright fraud, it's definitely scientific misconduct. As well as Fleischmann and Pons and the university administrators who pressured them into releasing their work before it was ready, and then tried to sell it to the government for millions of dollars before it had been confirmed, the news media does deserve a little of the blame for running with the story despite the discrepancies. I often wonder how much trust in science is damaged by the people who write headlines. If the headlines, especially in some of the trashier newspapers, are all that you ever glance or skim over, you'll get the impression that scientists are the biggest bunch of fantasists and hype merchants that you've ever seen. Hardly a week goes by without some headline reporting on some world-changing discovery, aliens or fusion or room-temperature superconductors or an asteroid that leads to the end of the world, and quite often this is attributed to just scientists, as if science is a nebulous community with all of the opinions uniformly spread amongst all scientists. More often than not, though, they're misquoting the scientists, identifying fringe science as part of the mainstream, and massively simplifying or exaggerating the findings. Everyone needs clicks, and everyone needs traffic, and everyone's attention span is about 3 seconds long, and it's good, I suppose, that people are writing about science instead of just endlessly dissecting the Game of Thrones finale for clicks. But it can't help but undermine people's confidence when this is what they see, and nothing ever seems to result from it. You can say that the journalists didn't understand the science, and perhaps this was a genuinely, entirely new phenomenon, so no one in the world really did. That's true enough. But even if you don't understand the science, it's best to be cautious. Here's a fact about the cold fusion fiasco I didn't really appreciate, from Frank Close's book Too Hot to Handle. As we discussed, the secret ingredient for Fleischmann and Pons' fusion cells was palladium, the catalyst that, in their theory, allowed deuterium to fuse. But palladium is a rare element, difficult to mine and extract. People looking to replicate the Fleischmann and Pons experiment were already running into difficulties in obtaining palladium, while the Fleischmann and Pons cell only produced a small amount of heat. Claiming that cold fusion, then, was the source to limitless energy is incorrect. The amount of palladium being mined at the time was only enough to perhaps power a small, medium-sized power plant. So even assuming cold fusion was real, you could dismiss the idea that it would power the world overnight with simple back-of-the-envelope calculations. To all intents and purposes then, cold fusion, born in that press conference on the 23rd of March 1989, was dead by the end of April 1989. By then, dozens of separate problems had been found with the initial experiment. Various groups had tried and failed to reproduce the findings, which would of course be necessary if cold fusion was to be useful anyway. After all, if it's incredibly difficult to get these reactions set up and only Fleischmann and Pons have the magic touch, you can hardly say it's going to change the world. But all of these replications and all of these errors that had been found made it even more likely that the results were indeed an error. Combine that with the fact that they flew in the face of all known physics and would require new and unlikely phenomena to take place, even though this type of apparatus had first been investigated in the 1920s, and there really wasn't much to recommend cold fusion from a scientific point of view. But the same combination of factors that led to the initial announcement also led many of the protagonists of the cold fusion story to double down. The well-known idea that a lie can get around the world before the truth gets its boots on is true in the sciences as well. And Fleischmann and Pons, in the face of mounting evidence that they made a catastrophic mistake, remained true believers in the phenomenon that they thought they discovered. They took with them a very small cadre of other researchers who had become intoxicated with the success and the excess heat of neutrons that they thought they'd seen, and the promise that, if only they could get this process to work just right, they might yet achieve the fame, the billions, the scientific progress, the boundless source of energy that they've been looking for. The state of Utah, where the two main cold fusion experiments had been conducted, ploughed an extra $5 million into the research, creating the National Cold Fusion Institute. Isolated groups continued working on cold fusion well into the 1990s. The US government gave up, and the National Cold Fusion Institute shut down by 1991. Fleischmann and Pons themselves were employed for several years by the Toyota Corporation in Europe, before they eventually also grew tired with the lack of results. Similarly, many of the Japanese corporations that had looked into cold fusion at the start had all shut down their research by the mid-1990s after spending millions of dollars. Since then, there have been sporadic bursts of activity. In 2004, for example, the Department of Energy organised another review into the state of play in cold fusion research. And even though the review concluded that the effects are not repeatable, the magnitude of the effect has not increased in over a decade of work, and that many of the reported experiments are not well documented, many cold fusion advocates were at least happy to have their work given serious consideration by the government, even if the government did just pan it for all of its mistakes. In 2012, in an echo of other research into fusion by Penthouse magazine founder Bob Guccione that we talked about, the billionaire Sidney Kimmel watched an interview with a physicist about cold fusion on CBS News, and became convinced that cold fusion might be a road to energy production. He invested another $5 million in the Low Energy Nuclear Research Department at the University of Missouri, which it appears has since been disbanded with its first director claiming to no longer believe in cold fusion. There are still communities of cold fusion researchers to this day, although they usually prefer to avoid talking about the cursed formulation of cold fusion and talk instead about low-energy nuclear reactions or catalysed fusion reactions to avoid the stigma associated with the disaster of 1989. Some of them publish in legitimate scientific journals from time to time, many more publish in illegitimate scientific journals and hold conferences in the same kind of venues as UFO truthers and 9/11 conspiracy theorists. And their websites are often very similar, trust me, I've seen plenty of them. In a lot of cases, there's a cult-like mentality of pathological science. It's motivated more by a desire to be right where everyone else is wrong, and resentment towards the perceived arrogance of the mainstream scientific community, than any actual new results or developments in the field of late. And there has been another 30 years of various people researching this thread. It's difficult to say what else they're hoping to find. Prominent amongst these is Andrea Rossi's ECAT device, which we dealt with on the thermodynamics episode on free energy scams. It is fascinating to me that you can still go online and see forums full of people quite seriously debating which form of cold fusion is the superior option for satisfying the world's energy needs, while ignoring the fact that the whole phenomenon appears to be an illusion at worst, and at best a reaction that has very little to do with any nuclear reactions whatsoever. At best, this research might lead to some interesting new chemistry. I don't mean to say that there's no interest in studying electrochemistry, and even potentially energy liberation from electrochemistry. Fleischmann and Pons had very productive and successful scientific careers doing just that, before they fell down the cold fusion rabbit hole and wrecked it all. But Rossi, who is often held up as one of the leading lights of this movement online, is an obvious fraudster. His so-called ECAP device makes use of a fusion reaction that's even more energy intensive than the one claimed by Fleischmann and Pons. If it worked, everyone stood nearby would be killed by gamma radiation from the reactor. He's never demonstrated the device in public without it being plugged into the mains. It's never been subjected to any proper peer review for the decade that he's been plugging this nonsense. Perhaps most damning, though, is the fact that Rossi has been trying to pull versions of the same con for his entire life. In the 1970s, he claimed to have a company that could produce oil from industrial waste, but this scheme was exposed as a fraud and he was imprisoned. In the early 2000s, he was employed to produce thermoelectric devices that produce electricity from heat, that performed less than 0.1% as efficiently as he claimed they would. Now he's flogging cold fusion. So if this is the public face of your movement and the source of all these conspiracy theories, then you need to take a serious look at yourself in the mirror. I'm sure that there is at least a few of you out there who think that I'm being excessively harsh to cold fusion and maybe displaying some of that arrogance that has led people to be alienated from the mainstream of science. Charles Safer attributes the longevity of cold fusion scandals to this reaction, which some people saw as knee-jerk. He said, quote, "The outrage over how Fleischmann and Pons were treated helped to keep cold fusion alive. The smackdown in May had the air of a public lynching. In its wake, the climate in the physics community turned from scepticism to scorn. So a number of people inevitably leapt into the fray on the side of the underdogs." There are understandable reasons to want to believe in the underdogs. Any newspaper or article writer dealing with cold fusion isn't going to get a headline out of saying, "Cold fusion remains dead." This show would probably get more listeners if I was claiming to hold the secret to unlimited energy, but I was being brutally repressed by an arrogant scientific establishment that couldn't accept that they were wrong, rather than telling you the truth, which is that I don't have any secrets at all. Conspiracy theories in subsequent years were further fueled by a cold fusion scientist killed in an explosion during one of his experiments, and another physicist and science writer who had supported cold fusion being murdered outside his home in 2004. He was killed by someone who he'd just evicted from that house as he was preparing it to be rented, along with their accomplices, and all of the people who killed him are now in jail, but it hardly helps to dampen down a conspiracy theory when someone is mysteriously murdered. But the reality is that the claims of cold fusion advocates simply don't hold water. Across the world, across various nations, various organisations, hundreds of millions of dollars have been spent pursuing this phenomenon, chasing this phantom. 3 decades of scrutiny has been given to the claims of cold fusion advocates, and it remains on the fringe for good reason. If this seriously seemed like a viable way of getting energy, don't you think genuine research institutions would be looking into it? Extraordinary claims, like the idea that you found something new in your test tube experiment that contradicts all known physics about nuclear fusion, require extraordinary evidence. And if you want to overturn the scientific paradigm, you need to be persuading people that you are correct. The evidence that nuclear reactions are genuinely going on is extremely thin on the ground. As for the small amounts of excess heat that are observed in the reaction, if they're not errors in measuring heat, they might just be some kind of chemical reaction or results from the electrolysis. None of these millions of dollars in experimentation has been able to reliably reproduce these heat excesses, and no one has built any kind of useful device using these reactions. I imagine if every potential candidate for, say, a battery got the same degree of scientific attention and funding as cold fusion had, then we would probably have far more interesting phenomena to talk about than the strange phantom that was discovered by Fleischmann and Pons. And it's in this that cold fusion is really frustrating. In some ways it should be seen as a success story for the scientific method. A claimed new discovery was made, it was tested and peer-reviewed, and it was ultimately found to be lacking in merit, so it wasn't pursued. All of this could have happened in the short space of a few weeks. If Fleischmann and Pons hadn't held their press conference and had instead tried to publish their stuff in Nature to begin with, then maybe the controversy would never have made it into the mainstream at all. Yet instead, millions of dollars and many years of effort from otherwise talented scientists have been poured down this particular drain without any progress being made. Now, especially in the Buzzkill episodes, I've made it clear that some people view magnetic confinement fusion or inertial confinement fusion efforts as a waste of money because they haven't realised any net power yet. Indeed, there is a certain parallel between cold fusion researchers and other fusion scientists, not in their scientific rigour or the merits of their science, but in the fact that they're all intoxicated by a similar dream, even as people sneer and say that it's impossible or that they've been promising too much for too many years. It's a noble dream of a clean future where cheap energy liberates us from environmental destruction, lifts people out of poverty without contributing to climate change or depleting resources. In that sense, in that dream, there are similarities. But at least genuine nuclear fusion can point to real progress, real data and real measurements. Confinement times have gone up, our understanding of the ways plasma can behave has improved, energy production has risen with each new generation of devices, and we've developed new devices, new measurements and new technologies as a byproduct of the research. The fact that it might not be commercially viable doesn't mean that it's bad scientific research. It might just make it a bad investment in the next few decades if you're interested in something mainly to make a whole stack of money. But of course in the long term, who knows, maybe it will become more viable. But cold fusion has no such success story. There have been no developments in the devices or experiments used. There's no consistent theory of what's going on in these reactions. They've done little to enhance our understanding of nature, and they have little prospect of ever working out. Mainly because the fundamental ideas behind them are without much scientific merit. The field essentially exists and survives on that dreamy nostalgia and that delusion that began in 1989. If Fleischmann and Pons had only done the right thing, published only results that they were sure of that could be produced consistently, and done it through the proper channels, then there would be no need for episodes on cold fusion because no one would ever have heard of it. The whole affair has instead damaged the credibility of science and surely done more to hold back scientific development than many other experiments you can name. The thing that it's most valuable for is as a cautionary tale for future scientists. It takes a great deal of evidence to be genuinely sure that you've discovered something brand new and phenomenal. You should be open and honest in your research, expose your claims and experimental method to repetition by others, and gracefully accept when you made an honest mistake. Otherwise, there is nothing for your theory but to become another embarrassing byword for pseudoscience. It may seem harsh, but we're looking for the truth here, and this is what works. So it's time for a quick overview of where we are and where we're going in this marathon nuclear fusion series. So far we've followed fusion from its first theoretical underpinnings, through the hydrogen bomb and early experiments, the tokamak revolution that came along, the jet tokamak that came the closest to producing net energy. The ITER-tokamak collaboration between the US and the USSR was agreed towards the end of the Cold War, as the next generation tokamak that would be the first to achieve scientific break-even. All the while, however, growing concern that fusion could ever be commercially viable on scale with these machines led to magnetic confinement fusion facing competitors, from some realistic sources like laser fusion, and some less realistic ones like the cold fusion that we've just described. Over the next few episodes we'll talk about inertial confinement fusion, how it developed, and the story of the National Ignition Facility, the largest laser fusion experiment yet attempted. We'll also discuss the ITER project, its inception, how it's developed over the years, and taking us right up to the present day. Alongside that, I'll describe some of the many startups and companies like Lockheed Martin that are trying to, in the modern era, outflank ITER by producing fusion in some other means. Some of them tokamaks, some inertial confinement, some entirely new. Alongside other magnetic confinement experiments like the Wendelstein stellarator in Germany that are reviving old ideas. So in short, we're going to bring fusion right up to the present day, and then look at its prospects into the future. I don't know how long I'll keep doing this show, but I hope for a very long time. And if that's the case, perhaps we'll be able to come back in a few years when ITER is switched on and see how all these predictions pan out. And of course we'll also be able to see how well the various startups we're profiled are doing. That's all in the future though. We're nowhere near done with the past just yet. I'll see you next time. Remember, you can find us on the web at www.physicspodcast.com, where you'll find the contact form, where you'll find ways to comment on each of the episodes, ways to review the show, where you'll find ways to donate to the show if you want to support us financially. The best thing you can do, though, is send us a message telling us what you like, what you didn't like, comments, questions, concerns, and tell as many people as you can about the show. Until next time, then, take care.
you.